Let us continue chemical equilibrium. Now in the chemical equilibrium, we will go for relation between vapor density and degree of dissociation. Vapor density and degree of dissociation, that relation we will see. Now, first, what is meant by degree of dissociation, that we will see. What is meant by degree of dissociation, that point we will see. So, we are seeing what is the meaning of a degree of dissociation. Degree of dissociation. For this, what is the symbol alpha? Alpha is the symbol. Degree of dissociation symbol is alpha. What does it mean? That we will see. Now we will take a N2O4. We will take N2O4. We will take this N2O4. We will take suppose some 5 moles we are taking. Some 5 moles we are taking. This is undergoing dissociation. This on dissociation gives a NO2 gas. NO2 gas. So initially we are not taking any NO2. We are taking only N2O4 initially. How much N2O4 dissociating till equilibrium, in the sense 3 moles. 3 moles of N2O4 dissociating till equilibrium. So how much N2O4 remaining? Remaining number of moles is 2 moles. So at equilibrium 2 moles of N2O4 is remaining. How much N2O4 dissociated, in the sense 3 moles dissociated? How many moles of N2O4 taken initially? That is 5 moles. Now 3 moles of N2O4 on dissociation gives how many moles of NO2? That we have to see. Now 1 NO2 on dissociation gives 2 NO2. 1 N2O4 on dissociation gives 2 NO2. So 3 moles of N2O4. 3 moles of N2O4 on dissociation gives how much NO2? 6 moles of NO2. 6 moles of NO2. Okay. Now we will see degree of dissociation of N2O4. That means degree of dissociation symbol alpha. Alpha of N2O4 we will see. Alpha of N2O4 is equal to number of moles of N2O4 dissociated. Number of moles of N2O4 dissociated by initial number of moles of N2O4. Initial number of moles of N2O4. Okay. Degree of dissociation of N2O4. Degree of dissociation of N2O4 is equal to number of moles of N2O4 dissociated by initial number of moles of N2O4. Okay. Sorry. Number of moles of N2O4 dissociated is 3 moles. Okay. Initial number of moles of N2O4 is 5 moles. Therefore, equal to how much, in the sense 0.6. Therefore, degree of dissociation of N2O4 is 0.6, we can say. Now, what is the maximum value of degree of dissociation? That we'll see. What is the maximum value of degree of dissociation? That we'll see. Now, maximum value of degree of dissociation. This is maximum in the sense denominator we cannot do anything, but numerator we can do maximum. Okay. So denominator we cannot do anything, but we can make numerator as maximum. So if you want to maximum alpha, that means if you want to raise the alpha, if you want to raise this alpha value, which we have to raise? This numerator we have to raise. Denominator we cannot do anything. Denominator we cannot do anything. Okay. So numerator we have to raise. So if numerator rises, then we can say this alpha rises, we can say. If numerator number of moles of N2O4 dissociated, this numerator rising, in the sense we can say degree of dissociation rising. Sir, this numerator will attain maximum. This numerator will attain maximum value. How much? That is equal to how much? Initial. That is equal to what? Initial. So maximum value of numerator is equal to initial means what does it mean? Complete dissociation. That is the mean. Okay. So now we will see complete dissociation. We'll see. Okay. Now we'll go for this. Here complete dissociation will take. Now, so initially we took 5 moles of N2O4. Now we are taking complete dissociation. Complete dissociation. Complete dissociation means how much we have taken, that much should undergo dissociation. So how much remaining? 0. Isn't it? So how much NO2 is produced? That we will see. Now 1 mole of N2O4 on dissociation gives 2 moles of NO2. So 5 moles of N2O4. 5 moles of N2O4 on dissociation gives 10 moles of NO2. Okay. Now, maximum alpha we'll see. Now, number of moles of N2O4 dissociated is how much in the sense 5. Initial number of moles of N2O4 how much means 5. Therefore, alpha is 1. So maximum value of alpha is how much in the sense 1. So degree of dissociation, maximum value is how much means 1. Generally, what is the degree of dissociation value in the sense less than 1 we can say, greater than 1 not at all possible. Why alpha cannot be greater than 1? Okay. How numerator can be greater than denominator? Is it possible? Numerator means the number of moles of N2O4 dissociated. That maximum value is how much? Initial number of moles. Numerator cannot be greater than denominator. Therefore, alpha cannot be greater than 1. So, degree of dissociation, maximum value is how much means 1. Generally, degree of dissociation will be less than 1, we can say. So, now what is the degree of dissociation we got? Now, we will go for relation between vapor density and degree of dissociation. So, now we are going for vapor density, degree of dissociation relation. Okay, relation between vapor density and degree of dissociation we will see. Okay, now let us take reactant A. That on dissociation gives B. How many times B means suppose Y times. Okay, now initial initially we are taking A. How much means 1 mole of A we are taking. We are not taking B. So this in A is dissociating. How much dissociating in the sense alpha is dissociating, degree of dissociation. If denominator is 1, okay, if denominator, you now see, if denominator, this denominator is 1 means how much dissociating, that is called degree of dissociation, isn't it? So degree of dissociation is equal to number of moles of N2O4 dissociated if denominator is 1. Correct? So if denominator is 1, then we can say alpha is equal to number of moles of N2O4 dissociated. So we can say initial moles is 1 mole. Therefore, how much dissociated means alpha is dissociated. Degree of dissociation is dissociated. Okay. So at equilibrium, how much will be there? That we'll see. At equilibrium, initially 1 mole we have taken. Alpha moles dissociated means disappeared. So remaining is how much means 1 minus alpha mole. 1 minus alpha mole is there. Okay. Now how much B is there? We'll see. See, 1 time A on dissociating gives Y times B. So 1 mole of A on dissociation gives Y moles of B. So here how much A is dissociating? Alpha moles. Alpha moles of A is dissociating. Okay. Alpha moles of A is dissociating. Therefore, how much B will get? Y alpha will get. Okay. So B we are getting a Y alpha we are getting set. Now we will consider initial moles. Initially how much A we have taken in the sense 1 mole of A we have taken. 1 mole of A we have taken. That volume is how much in the sense that volume is a V liter will take. That volume is V liter will consider. So at equilibrium we'll see. Now total moles at equilibrium we will take. Total moles at equilibrium means 1 minus alpha plus Y alpha. How in the sense A is 1 minus alpha present at equilibrium, B is Y alpha present at equilibrium. So at equilibrium, what is the total moles in the sense A 1 minus alpha, B Y alpha. Okay, total moles this much. Now, this is at equilibrium. Now we will see volume of equilibrium mixture. Volume of equilibrium mixture we will see. Volume of equilibrium mixture is how much we will see. See, for 1 mole volume is V means for this many moles, what is the volume? 1 minus alpha plus Y alpha into V. This is the volume. Okay, this many liters. For 1 mole, volume is V means for this many moles, what is the volume? 1 minus alpha plus Y alpha into V. Okay, sir. So we got a volume. Here, what you have to do means pressure, temperature remains same. We have to take pressure of system remains constant, temperature of system remains constant. Then we can say number of moles is directly proportional to volume. Okay, so 1 mole means V. 1 mole volume is V means this many moles volume is, we have to multiply this number of moles with the volume. Okay, sir. So this is how in the sense we know Avogadro's law, V1 by N1 is equal to V2 by N2. Okay, so based on this we can find. So initially V1 is how much? V. In V1 is V. The N1 is how much? 1 mole. Okay, that 1 mole will substitute. Then V2 we want. N2 is how much? This many moles. That is 1 minus alpha plus Y alpha. Y alpha. Now V2 is how much? These two cross multiply, you will get V2. Okay, so we got this volume. Okay. Next point we'll take a molar density. Molar density before equilibrium. Molar density before dissociation. Molar density before dissociation is equal to what in the sense? Molar density before dissociation. Molar in the sense 1 mole. So before dissociation, what is there? A is there. So take A, take how much A you have to take in the sense 1 mole of A you take, that mass you take. So mass of 1 mole of A we can say. Initially we are taking A only. So mass of 1 mole of A by volume we have to substitute. Volume of 1 mole of A we have to substitute. We have to write. Okay. So volume of 1 mole of A. Volume of 1 mole of A. Okay. So volume of 1 mole of A we have written. Okay. So density, what is the formula of density? Mass by volume. Molar density means for 1 mole. Okay. Therefore, mass of 1 mole of A we have to take by volume of 1 mole of A we have to take. Why you are taking only A? Why you are not taking B? Because before dissociation. Before dissociation, what is there? A only is there. Therefore, we are taking like this. Okay. Sir. So this is called what in the sense? Molar density before dissociation. Okay. This is equal to what in the sense? Capital D we can take. Okay. So molar density before dissociation is a capital D we have taken, that is equal to this much. That is equal to so and so we can say. Okay. Next, we will take a molar density after dissociation we will take. Now we will go for molar density after dissociation. Molar density after dissociation, that is equal to what we will see. So molar density after dissociation, that means density in the sense mass by volume. So we will write mass by volume, we will write. Mass by volume we have written. So mass of what we have to take? Mass of what we have to take? Mass, the molar density after dissociation means mass of what we have to take? Mass of, say, after dissociation means the system is at what? At equilibrium. System is at equilibrium. Set. So system is at equilibrium we can say. So system is at equilibrium in the sense. Here what we have to substitute? System is at equilibrium. Therefore, a mass of 1 mole of equilibrium mixture will take. Okay. Mass of 1 mole of equilibrium mixture by volume of 1 mole of equilibrium mixture. Volume of 1 mole of equilibrium mixture. Okay. So mass of 1 mole of equilibrium mixture by volume of 1 mole of equilibrium mixture is called molar density at equilibrium. Set. Now, instead of writing like this, in the numerator, I will write mass of 1 mole of A. Mass of 1 mole of A I will take. Mass of 1 mole of A if I take. Okay, mass of 1 mole of A I have taken. This is nothing but what in the sense? This is nothing but what in the sense? Mass of 1 mole of A. What is the meaning of that in the sense? Mass of 1 minus alpha plus Y alpha moles at equilibrium. At equilibrium. Okay, that is the meaning. How do we say like this? Now we will see. Here initially what did you take? 1 mole of A. At equilibrium what is there? 1 minus alpha of A and Y alpha B. Now what is the mass initially? That is the mass at equilibrium. At equilibrium, that means total moles at equilibrium is there no here. Total moles at equilibrium is equal to 1 minus alpha plus Y alpha we have written no. This total mass and initial mass will be equal. Big law of mass action. Okay. So initially 1 mole of A we have taken, that mass you consider. At equilibrium total moles is how much in the sense 1 minus alpha plus Y alpha. This mass, this at equilibrium, this mass, initial mass, both are what? Equal. Therefore, mass of 1 mole of A is equal to mass of 1 minus alpha plus Y alpha moles at equilibrium. Okay, sir. So now we can say mass of 1 mole of A is nothing but mass of 1 minus alpha plus Y alpha moles at equilibrium. So now volume we'll see. Volume of mass of 1 mole of A is nothing but mass of this many moles of A and B, both A and B. Okay. So denominator what we have to write means volume of this we will substitute. Volume of this we will substitute. Volume of 1 minus alpha plus Y alpha moles at equilibrium. Moles at equilibrium we will substitute. Okay. So denominator we have substituted like this. So numerator what we can say in the sense mass of 1 mole of A means gram molecular mass of A. Volume of this is a denominator volume of equilibrium mixture in the sense 1 minus alpha into plus Y alpha into V. This is what in the sense a denominator. Denominator volume is this much. So denominator volume is how much in the sense 1 minus alpha plus Y alpha into V. This is equal to molar density after dissociation. So molar density after dissociation we got. Okay. Now capital D is called molar density before dissociation. Small d is called molar density after dissociation. So capital D we will substitute. Capital D is how much in the sense mass of 1 mole of A by volume of 1 mole of A. Mass of 1 mole of A we can say gram molecular mass of A. Volume of 1 mole of A is given here. That is how much in the sense V liter. So V liter will take this we will substitute now. So capital D is gram molecular mass of A by volume of 1 mole of A. Small d is gram molecular mass of A. Gram molecular mass of A by 1 minus alpha plus Y alpha into V. Okay. So what is getting cancelled? You see, cancel it. What is the remaining term that you write it? Therefore, capital D by small d is equal to 1 minus alpha plus Y alpha we can say. Okay. So capital D by small d is equal to 1 minus alpha plus Y alpha we can say. Here we can take alpha common. Therefore, if you take alpha common, you will get Y minus 1. So like this we are getting. Therefore, now from this relation, we can say that alpha is equal to capital D minus small d by small d into Y minus 1. We can say. Okay. So now capital D is called what in the sense vapor density of A. Small d is called vapor density at equilibrium, vapor density of equilibrium mixture. Okay. So capital D is called vapor density initial, vapor density of A. Capital D is called vapor density of A. Small d is called vapor density of equilibrium mixture, vapor density of equilibrium mixture. Small d is called vapor density of equilibrium mixture we can say. Okay. So this y is called what in the sense y times b we got no. This y is called this is y, that y is this one. Okay. Now we will consider some example. We will consider what is the y value that we will see. Now if a PCl5 gas gives PCl3 gas plus Cl2 gas. Now, what is the y value in the sense PCl3 1, Cl2 1, therefore y is equal to 2. Like that we can say. Okay. Now, suppose we will take a 2NO2 gas gives N2O4 gas. N2O4 gas. What is y? Y is equal to how much in the sense this one only y. Okay. This we have to make it as 1 mole. Then only we will get this y. Because A gives YB only we said no. Therefore, you make this is as 1. So, NO2 gas gives of N2O4. Of N2O4. Therefore, y is equal to 1 by 2. Okay. You have to make this as 1 mole. And how much this is there you have to see, that is y. Okay. So, that is why we got an idea. Sorry. Now, theoretical part of chemical equilibrium is completed. Now we will go for sums. We will go for sums.